Welcome everybody to this new lecture of the class Complex Analysis. What is the goal of this lecture? We want to study holomorphic functions as transformation of the complex plane. So let me give an introduction to what we mean by this. Of complex plane. So let me introduce this problem. So we consider here an open set U and a holomorphic function defined on U. And what we want to study is how this function f transforms point of U into a point in C. So we can think of U as lying in the complex plane with coordinate x, y. So U will be some open set, maybe something like this. So here in the interior, this is my U. And now we refer to a point in U as Z. So this will have coordinate x plus I, y. And we call this plane where U lives the Z plane. Then my function f maps point of view into complex numbers. And these complex numbers we can also visualize using the plane, but this time we will use coordinates U and V to distinguish between the starting coordinate x, y, and the ending coordinates. So the points here will be denoted by W, and these have representation U plus IV, so this will be called the W plane. So what is the problem we want to consider? Is how to visualize this transformation. So F associate to Z, a W, so we can think of this W as F of Z. And we want to understand how to visualize this transformation. So we want to visualize how F transforms the point of the set U. And here, let me remark that this is in general a bit difficult to visualize. So this is difficult because we cannot simply draw the graph of F. Also difficult because we cannot draw the graph of F because this is a set of pairs Z, F of Z, such that Z lives in U. But this is a subset of C times C, and this is a four-dimensional object. So this would require 4 dimensions. So we cannot surely do this in a simple way. As we would do, for example, if we have a real function of a real line, then you know that to visualize this function, you can simply draw the graph and you can draw this in the plane. But for complex functions, like holomorphic function, this is not that easy because we would require too many dimensions. So how are we going to have at least an idea of what this function f is? So the idea is to consider one-dimensional objects. So consider curves C in the set open set U and study how these curves are mapped by F and study their images. F of C in the W plane. So let me, before seeing this in an example, let me recall how we can define curves. So the curve in this picture will be something maybe like this. This is my curve C. And then we will get an image here under the map F. But how can we describe curves? We can describe curves by parameterizing them using a function from an interval. So let me recall this. A curve is a set C given by the points gamma t, where t lives in some interval AB, and gamma is a function from AB into U, which is differentiable in our case. Now, this means that the derivative exists at every point, so gamma prime of t exists for all t. And this means that the image f of C is given by f of gamma of t, where t lives in this interval A and B. Okay, so in this case, we get a real an honest parameterization of the curve given by gamma. So we also have here an orientation of the curve because the interval is oriented, so we can go from small t to big T, and this gives us also an orientation of the curve. So the point Z here, then it's gamma t for some t. And then here you see, you get the point F gamma t in the image curve. So let me then give an example where we can see how F transforms these curves. The example is taking as F the our tool. So F goes from C to C and is given to Fz equal to z squared. So in this case, the open set U is the whole complex plane. And now we want to understand the image of some curves. So the easiest thing to do would be to take as curves the lines which are parallel to the axis. So let me take here the origin in the z plane, and then I can consider, for example, horizontal line. This is my C. And let me take, for the moment, this line not passing through the origin. So for L, which is a real number different from 0, we take as C all the points x plus I, y, such that the y coordinate is equal to L. So this is the curve we are considering here. And now, how can we parameterize this curve? So this is easy. So the x coordinate is free. So this is a variable t, and then the y coordinate is fixed, so IL. Now let's see what is the image of this curve. So f of gamma of t, this is t plus IL squared. And the computation gives us t squared minus L squared plus 2TL times I. So here we see there are two coordinates. The first coordinate is U of t, And the second coordinate is the coordinate v of t. So in the new coordinates, we have t squared minus L squared and 2TL. So in order to understand what kind of curves is this, let me eliminate t from these two equations. So this can be done by using the second one. So from the second equation, you see that t is equal to v of t divided by 2L. And here you see why I'm taking L different from 0. Then if I substitute in the first equation, I get u of t equal to v of t squared divided by 4L squared minus L squared. Okay, so now here we can read off what this curve is. So this curve, f of c, these are all the u plus iv, such that 4L squared times u plus L squared is equal to v squared. Okay, so maybe let me draw this. So here above we have the Z plane, and then let me draw here below the W plane with the origin somewhere here. And now this curve f of c can be seen easily that this is a parabola with horizontal axis. Now you can compute where the vertex is and everything. And it will be something like this. Okay, so that's the u axis as axis of symmetry, and you see the shape depends a bit on the value of L. Also, for example, if I take L very close to 0, then this parabola will come here very close to the positive u axis. And then also you can see the parametrization. So above we are going from left to right, then in the W plane, what happens when t is negative, then in the above case, L is positive, so V is also negative. So in the below, we are going also in this direction. Okay, so this is what happens to the curves parallel to the x-axis. Now we can do same job for curves which are parallel to the w-axis. So this, maybe I can call this curve C tilde. And this curve C tilde can also be written. So let C tilde equal to the points x plus I, y, with the property that now x is fixed, is equal to some k, where k is also a real number different from 0. Then we can do a similar computation as above, and we will find out that f of C tilde, these are the u plus iv, such that minus 4k squared u minus k squared is equal to v squared. Okay, so this is also the parabola with the horizontal axis, but now in some sense is mirrored. So we have now a parabola going in the other direction. Okay, so, and also here, one can see that when C is negative, then we also have V negative. So we have something like this. So this is also very interesting because, for example, notice that these two curves, C and C tilde, have an intersection point, C, small c here. But the corresponding curves in the W plane have two intersection points. So the point C actually corresponds to the point here above. This is f of C. And the other point corresponds to the fact that the function f is not injective. So here you can find 2 points which are opposite to each other. More or less here in the picture, this is the point D, and this is the point minus D. And then when we take the square, they go to the same point, and this is the point here below. Now this is the point f of D equal to f of minus D. And from this picture, one can see also a general phenomenon that now we are going to prove, is that this function f preserves angles. What I mean by this, you see C and C tilde are orthogonal lines. So here we have an orthogonal angle. And then the same happens here. So also these curves, f of C and f of C tilde, meet orthogonally at the intersection point f of C. And now we are going to prove this in general. And this will be very important geometric property of holomorphic functions. So we have now part B. This is the preservation of oriented angles. So let me define what is the oriented angles between two vectors first. So 2 points in the plane which are non-zero. So let me take P1 and P2. These are points in the complex plane without zero. And we can think of this as two vectors in the plane. So we have here 0, and then the first vector P1 maybe something like this. And the second vector P2 maybe something like this. And then P1 will have some polar coordinate decomposition, R1 times EI theta 1. And the same for P2, we will have R2 times E to the I theta 2, where theta 1 is this angle and theta 2 is this angle. So if we are interested in the angle between the two, this is a bit, so if we are interested in the angle between the two, so this is the angle here in between, then this angle is simply theta 2 minus theta 1. So we can give the definition, the oriented angle between P1 and P2 is given by P1, P2 with a hat above. This is the notation I use. And it's simply theta 2 minus theta 1. And this is well defined up to multiples of 2 pi. Because theta 1 and theta 2 are also well defined up to multiples of 2 pi. Why do I mean that the angle is oriented? Because here I'm thinking of the angles as increasing in the counterclockwise direction. So we are taking here theta 2 minus theta 1. So this means that this angle, I'm thinking the angle of going in this direction. So if I reverse the role of P1 and P2, I will get minus the angle between pi2 and pi1. So notice that the angle between P1 and P2 is minus the angle between pi2 and P2 and P1. Okay, this is because the angle is oriented. So we are always thinking we are rotating P1 in the direction of P2. So let me now state a simple lemma showing how we can express this angle in an equivalent way. So the lemma says that the angle between P1 and P2 is the argument of P2 divided by P1. Okay, so this is immediate to show. So just use the definition of P2 and P1 in polar coordinates. This was R2 e to the I theta 2 divided by R1 e to the I theta 1. And you see that this is R2 divided by R1. This is the new norm. And then we have EI theta 2 minus theta 1. And you see that the angle of this is exactly theta 2 minus theta 1. And this we stipulated to be the angle between P1 and P2. Okay, so this finishes the proof of this simple fact. So now we understand what is the angle between vectors. Now we want to define the angle between curves. So to do this, let me consider the following situation. So we take C, a curve. So let's see be a curve, which I assume now to be regular. Let me explain what it means regular. So this is a regular curve. This means that the derivative of gamma is different from 0 for all t in the interval a, b. Why is this condition important? Because if we have this condition, we can define the tangent curve. If T0 now is an element in AB, then L of T0, this is the line defined by gamma T0 plus S gamma prime of T0 for S real number. This is the tangent. Tangent to the curve C at the point gamma T0. Okay, so let me draw maybe a simple picture. So assume that my curve gamma is something like this. So this is my curve C, which is parameterized by gamma. And then we have on C the point gamma of T0. We are going here in this direction. Then the tangent line at gamma T0 can be drawn like this. This is the line L of T0. And you see this line has a direction which is given exactly by the derivative gamma prime of T0. So direction of L T0 given by gamma prime of T0. Okay, so this means that if I draw gamma prime of T0 and starting from the origin, well, this goes in this direction and gives me exactly the direction of the line L T0. So now this is when we have a curve. What happens if we take another curve? So assume C tilde parameterized by some gamma tilde T tilde from some interval A tilde B tilde is another regular curve. And moreover, we suppose that this curve intersects the first curve. So we suppose that gamma tilde of some T0 tilde is equal to gamma T0 for some T0 tilde in the interval A tilde B tilde. Okay, so this maybe means something like this, means that my curve C tilde is something like this, going this direction. And here you see gamma T0 will be equal to gamma tilde T0 tilde. And then for this curve, we can also define a tangent. The point, this is the curve L tilde T0 tilde. And so we also a tangent line L tilde T0 tilde to C tilde at the point gamma tilde T0 tilde. So here you see this curve is also as direction given by gamma prime, gamma tilde prime of T0 tilde. So here you also get this curve. This is the curve. This is the, sorry, the vector gamma tilde prime T0 tilde. And now the natural definition for an angle between these two curves would be to give exactly the angle between these two vectors, which is the same as the angle between the two tangents. So this is exactly what we are going to do. So let's give then the definition. Angle between C and C tilde at the intersection point let's call it C. This is the intersection point. So this is gamma T0 equal to gamma tilde T0 tilde is definition the angle between the two tangent vectors. So this is the angle between gamma prime T0 and gamma tilde prime T0 tilde. So this is the notation we saw before. Now, so this is in particular equal to the argument of gamma tilde prime 0 over gamma T0 tilde gamma prime T0. Okay, so this is was we showed in the lemma. Okay, so now the important property we want to show is that holomorphic functions preserve the angles between curves. So this is the content of the theorem with which we are going to finish this first part. So the theorem says that if we take F holomorphic and C and C tilde, two regular curves in U with intersection point C. So we assume that the two curves intersect. Then if f prime of C is different from 0, so this is important assumption. So if the derivative of f at the point C is different from 0, then the angle between C and C prime, sorry, C and C tilde at small c is the same, obviously up to multiples of 2 pi, as the angle between f of C and f of C tilde at the image point f of C. Okay, so this is the statement. So let me draw a picture of what we are saying here. So this is now my set U, where my function f is defined. And here we are taking two curves passing through a point. So the first curve maybe is like this. This is C. And then it goes through this point, small c. And then we have another curve doing like this. This is C tilde. And now we are considering the image under f of these two curves. This will be the curve f of C here, and the curve f of C tilde, and they meet at this common point f of C. And then what's that? This angle here is the same as this angle there. So this is what the theorem is saying. So let me give the short proof. So consider gamma and gamma tilde parametrizations of C and C tilde with the property that gamma of T0 is equal to C is equal to gamma tilde of T0 tilde. Then we get parametrizations for f of C and f of C tilde by composing with f. So f of gamma tilde are parametrizations of f of C and f of C tilde. And this parameterization, they meet at the point f of C gamma T0 is equal to f of C, which is equal to f of gamma tilde T0 tilde. So now let me compute the angle between f of C and f of C tilde at the point f of C. So what is this angle? So let's compute the angle between f of gamma prime T0 and f of gamma tilde prime at T0 tilde, the angle between these two vectors, which is by definition the angle between the two curves. So now by the lemma, this is the argument of the quotient between f of gamma tilde prime at T0 tilde and f of gamma prime at T0. So now we can use chain rule. So we are using here chain rule. And the two derivatives, so the derivative above is at the point gamma tilde of T0 tilde times gamma tilde prime T0. And below we have f prime of gamma T0 times gamma prime of T0. So now we use that gamma tilde T0 tilde is equal to gamma T0. So now we use that gamma tilde T0 tilde is equal to C, and also gamma T0 is equal to C. So now the derivative of f in C T0 tilde, but also below we are taking the derivative of f in C. Okay, so since f prime is different from 0, we can simplify, and what we get is the argument of gamma tilde prime T0 tilde divided by gamma prime T0. And we saw that this is the definition of the angle, sorry, by the lemma, this is this gives the angle between gamma prime T0 and gamma tilde prime T0 tilde. So this is this angle. And this is then exactly what we wanted to show. So we showed here that the angle between f gamma prime T0 and f of gamma tilde prime T0 tilde is the same as the angle between gamma prime T0 and gamma tilde prime of T0 tilde. And this is, by definition, the angle between the two curves. So this theorem shows us that the function f preserves the angles, and then to such functions, one gives the name of conformal functions. So this theorem says that holomorphic functions are conformal, namely preserve this function oriented angles. Okay, so we saw this in the particular example here above, with the function f of z equal to z squared. Here, this is reflected to the fact that the axes C and C tilde at the beginning, they meet orthogonally. And so they meet orthogonally also in their images. So f of C and f of C tilde, these are two parabola, and they all meet orthogonally. No? So here, all these angles, not only the one between the blue and the green line, but also the angles here, here, and here, they are all orthogonal. So this is the first part of the lecture, and in the second part, we are going to study some special holomorphic functions called Möbius transformation, which have better geometric properties. And we will see that this function will preserve lines and circles in the plane, which is a very useful property.